Hello everyone. Today we will be talking in depth about a useful circuit called a soft start circuit, or sometimes an inrush current limiter circuit. This video is pretty long, so if you're looking for something specific and don't want to watch the whole video, look at the chapters in the description to see what I go over in each section so you can skip to the section relevant to you. So what is a soft start circuit? A soft start circuit is a circuit that limits the current flowing from an upstream power rail into a downstream circuit during power-up so that the upstream rail is protected from being overdrawn or damaged by the current draw requirements of the downstream circuit. It may also protect the downstream circuit from damaging itself by drawing in too much current too quickly. It is primarily used in circuits with large input capacitances and when the input rail is abruptly applied or energized, or the manner in which the input rail is applied or energized is uncertain or uncontrolled. Soft start circuits tend to be important at the power input upstream of a significant amount of circuitry, such as a power rail in a large subcircuit or an entire circuit board, especially circuitry that has DC-DC converters in it. Soft starts are not generally applied to every chip or every small subcircuit, though many chips may employ their own internal soft starts as needed. Today we will be discussing 3 different soft start circuit design architectures, but first we'll talk a little bit about input capacitance for a DC system to give you an idea why such a circuit might need a soft start. I tend to usually talk about DC systems because they are the kind of systems I generally work on. However, inrush is present in AC systems as well, though the mechanisms for it are somewhat different. Though for AC systems that have a rectifier that feeds into a large input capacitance, inrush is remarkably similar to that of a DC system. So soft starts are often required for AC systems as well. Usually, when designing a board with DC-DC converters on it, you will have to incorporate a great deal of capacitance in the power system. Capacitance on the input side of DC-DC converters allows switching circuits like these converters to draw bursts of energy from the stored charge in the capacitor rather than having to draw the energy from the source, which is physically much further away and through inductance and resistance. As an illustrative example, let's say you have an AC adapter power supply providing 12 volts to a board which has a 5-volt buck converter on it. This 5-volt buck converter has a switching frequency of 1 MHz, which means it draws pulses of energy at 1 MHz from the switching action of the buck converter. The line from this 5-volt converter and the 12-volt AC adapter is going to be long, a few feet of cable and some onboard traces and planes. This is a long distance to draw current at 1 MHz, and drawing significant amounts of current will cause the V in voltage to droop due to the inductance and resistance of the cable wires, and may also cause significant electromagnetic fields to be radiated at 1 MHz along the long cable length, causing unwanted interference to other electronics. So, to mitigate this, we have this capacitor, Cin, here. The capacitor charges up to around 12 volts and serves as a local power source to the 5-volt converter. The loop of current at high frequency preferentially goes through this local capacitor, and there is much less impedance to the 1 MHz switching pulses, and much smaller loop area producing much lower electromagnetic interference and lower voltage droop. This capacitance is called input capacitance, and is also known as bypass or decoupling capacitance because it bypasses the upstream power source or decouples the circuit from the upstream power source. Input capacitance is not just used on power converters, it can also be used on anything that draws current at medium to high frequencies. In practice, we put some decoupling capacitance on nearly everything with a voltage rail. Similarly, there is a large amount of capacitance put on the output of this switching converter, along with a series inductor to filter out the pulsed output current. This capacitance is called output capacitance, or sometimes filter capacitance. The larger these two capacitances are, the better the reduction in electromagnetic interference, and the lower the voltage ripple due to the switching on the input and output rails. There are some trade-offs to making these capacitances too high, but that is beyond the scope of this video. Suffice it to say, having significant input and output capacitance is generally beneficial to the EMI environment and smooth operation of power circuits, and so we have to implement soft start circuitry to accommodate these capacitances at power-up. Now imagine the 12-volt AC adapter is plugged into the wall, and there's a cable from it that has 12 volts live voltage on it. When you plug that cable into our circuit there, you will instantaneously apply 12 volts to the discharged input capacitor. This will cause a massive surge of current into the input capacitor, because the cable resistance is very low, and so the RC time constant will likewise be pretty low, and so many amps of current will be drawn. This AC adapter may only be rated to output something like 2 amps, and trying to draw 30 amps from it, even for a short period of time, could damage it or cause it to go into a current limit safety mode. Additionally, the capacitor might not be designed to handle such a massive current going into it, and that might degrade the lifetime of the capacitor every time the circuit is plugged in. The output capacitance charging time can be controlled and slowed down by circuitry within the buck converter, but the input capacitance charging time cannot. And so we need a way to charge up this capacitance more slowly when the cable is plugged in, so that none of these bad things happen. The circuit that does this is our soft start circuit. So now that we've shown why soft start circuits are necessary in most large systems, let's go over the 3 design architectures I've selected for this video. The first soft start circuit we'll talk about is the simplest version, which consists of just using a negative temperature coefficient, or NTC, thermistor in series with the voltage input. This is such a common way of dealing with the soft start problem that there are many inrush current limiting thermistors designed specifically for this purpose. A thermistor is simply a resistor that's resistance is highly dependent upon its temperature. Negative temperature coefficient thermistors, for inrush current limiting, tend to have a roughly exponential dependency on temperature. The idea for this circuit is that this thermistor has a medium resistance when it's at room temperature, high enough to limit the current to below a safe level, but not so high that the current is negligible. But when you turn on the power rail, current flows into it, heating it up, and since it has a negative temperature coefficient, it will become low resistance at this higher temperature. During the initial phase, when the thermistor is heating up, the current flow is limited significantly, and the input capacitance is charged up slowly through this relatively high resistance. By the time the thermistor is hot enough to be low resistance, the capacitance is all charged up already, and the inrush phase is over. To explore this circuit, we'll use a CanTherm MF72-005D7 thermistor, which is about 50 cents on DigiKey. It's a simple 2-lead through-hole component that looks like this image here. Its datasheet says it is 5 ohms at 25C and about 283 milliohms at its rated current once it's heated up. Measuring it at room temperature with my DMM on resistance mode, I get between about 4.7 ohms and 5 ohms. It's very sensitive to the room temperature, so it's hard to pin down the exact value, especially since my DMM is a 2-wire measurement and thus not very accurate. And of course, touching it with my fingers heats it up, changing the value since body temperature is above 25C. After running 2.02 amps through it for a while with a current source and waiting for the resistance to stabilize, I measured resistance by measuring the voltage drop with my DMM, and I get about 0.6 volts in still air, which at a current of 2.02 amps is about 297 milliohms, which is pretty close to the expected datasheet value. Note that moving air around it cools the thermistor and causes its resistance to increase, so the actual value you'll get at 2 amps is very dependent upon air movement around the NTC thermistor and the actual temperature of the surrounding air. However, you usually don't want to run your parts at their maximum rated values, since going above the rated value may destroy the component or at least significantly reduce its lifetime. This is especially true if you don't know precisely what your downstream circuitry's current draw is or if it varies a bit. And so it's worth checking out what this thermistor's resistance is at 1 amp as well. With a 1.009 amp current source, I get a voltage drop of about 0.726 volts, which is a resistance of about 720 milliohms. So the resistance is highly dependent upon the current flowing through the circuit. This is a hint towards some of the disadvantages of this circuit. Now I've set up a simple test circuit with an approximately 11 ohm high power resistive load, a large amount of input capacitance, and a 12 volt input voltage. The steady state current is around 1 amp to 1.1 amps with this setup. We can see that given our thermistor's specified value of 5 ohms and our input voltage of 12 volts, we should expect the circuit to limit the input current to less than 12 volts divided by 5 ohms, or about 2.4 amps. Below is a picture of the setup on my breadboard, with my current probe measuring the current through the alligator clips, which are connected to my power supply. The switch that connects the power supply to the circuit that serves as the turn-on event is just me clipping the alligator clip to the thermistor lead. So I took a few scope shots and measurements of this circuit to see how it performs. First, we see the turn-on transient here, which peaks up at 2.167 amps, which is a little less than the predicted worst-case maximum of 2.4 amps. This is likely due to cable resistance bringing it down a bit. So, keeping the peak to a relatively low value was successful. It didn't blast up to 10 amps or brown out my power supply, and that peak comes down in about 50 milliseconds with a post-capacitance charge current of about 867 milliamps. This implies a resistance of about 13.84 ohms, which is higher than our expected 11.7 ohms. So the thermistor hasn't heated up in this small timescale yet, as this scope shot is only 450 milliseconds long after the initial turn-on spike. So I have another scope shot to show a longer time scale. I took this scope shot after shutting the system off and letting things cool down for several minutes for the thermistor to reset. I filtered and decimated the scope shot to make things much less noisy, as our bandwidth of interest is much smaller than the scope shot's bandwidth. Here we see that we reach a steady state current about 18 seconds after turn-on with a sort of asymptotic curve. For reference, here are the input and load voltages as well over that 20-second duration. We can see the voltage drop across the thermistor drops over the 20 seconds and sort of approaches close to its minimum around there. The final set of measurements I made was a bit more rough and by hand with my DMM, where I measured the resistance of the thermistor after removing power over a few minutes to see how long it took to return to about 5 ohms. It takes quite a bit of time, all things considered, taking a full 25 seconds to get up to around 2 ohms and achieving 4 ohms at around 90 seconds. So this thermistor takes about 20 seconds to reach a solid steady-state resistance, and over a minute to reset near its initial room temperature state. This can cause problems if you turn off the device and turn it on again only a couple seconds later, as the thermistor will not have reset and thus the circuit will not soft start. So I went in depth on this one thermistor, but to give you an idea of the resistance at load of a few different thermistor part numbers, I tested several of them. And the results are here. Note that my tests were under imprecise conditions, and the manufacturer's datasheet should be understood to be more accurate and reliable than my test values. Additionally, I only tested one component from each part number, so part-to-part variation is not accounted for. And very small changes in airflow, thermal environment, and room temperature measurably affect these values. And I did not take great care to keep the thermal environment stable, nor did I ensure to use whatever specific test conditions were called out in the datasheet, if any. I mostly just ran these devices at whatever temperature my lab was set to, and using my current probe to measure current, and waiting for the measured voltage drop to stop changing too much. It's worth mentioning that I lean towards the higher current options, as I tend to deal with projects that operate at relatively low DC voltage and have higher current. However, for projects operating at mains voltage, the currents tend to be much lower unless you have a very high power project involving a motor or some other power-hungry device. The max rated resistance at load can be much higher for a lower current project without causing problems, and thus the NTC Thermistor Soft Start just generally works better for circuits at lower currents. One final note on NTC Thermistor circuits. If you need more starting resistance, you can put multiple thermistors in series and get increased starting resistance at the expense of increased post-turn-on resistance. However, putting thermistors in parallel is a much different situation. The starting resistance will properly drop in parallel, however, post-turn-on only one of the thermistors will have heated up, because the one that drops its resistance more, even slightly more initially, will get more of the current from the input, which will cause it to heat up more and drop its resistance more, causing it to get more current, causing a kind of runaway effect. So one will be hot and the other will be cold in parallel. So if you put them in parallel to reduce starting resistance, that will work fine, but if you put them in parallel so you can handle a higher steady-state current, that will not work and they will get damaged. Similarly, if you want to reduce the on-state resistance by putting two in parallel, that won't work either. So in general, don't try to put them in parallel. There's not much point. Just try to find one that meets your needs. If you find one that meets your needs at steady state, but want a lower starting resistance, just put a normal power resistor in parallel with it, and that will work. Now that we've examined this soft start circuit, let's summarize its advantages and disadvantages. The NTC circuit is a very simple circuit. It is low cost, especially if your end circuit does not draw too much current, and it is very easy to calculate the approximate peak current for a simple capacitive load. I will admit it is a good choice if your steady-state current is low. The devices I looked at today were mostly on the higher current end, and the disadvantages become less of a concern under lower current conditions. Also, it works good for both AC and DC circuits. Current direction does not affect the system. On the disadvantages side, it has a high on-state resistance relative to something like a beefy power MOSFET or a relay. Recalling the table I showed, the minimum resistance I measured was only about 92 milliohms, and that was for the 10 amp version at its maximum current. The lower current thermistors had even higher resistances, and the half-max rated resistances were even higher. This leads to significant amounts of power dissipation that could make your system much less efficient than you might like. The dissipated power has to go somewhere, which causes the thermistor to get extremely hot. When I was running these tests, the thermistors gave off the smell of burning plastic at max current because they were so hot they were outgassing whatever residues were on them. Not only off-putting and causing burns if you touch the thermistor with bare skin, the high heat and fact that the resistance decreases the hotter it gets could result in thermal runaway causing a fire if a mistake is made during the design process and the thermistor is too close to something flammable. Tying in with this is also the fact that the thermal environment impacts the circuit significantly. If you insulate the thermistor too well, you might start a fire. If you heat sink it, or even if it's incidentally in the path of a fan intended to cool something else, it will be cooled down significantly more, and thus won't get its minimum resistance, resulting in burning off even more power. While I was testing these devices, I put a little shelter around the thermistor because I noticed that even when I just moved around the room, I got a noticeable change in the measured resistance. A fan blowing across the thermistor would have had a much greater effect. Most importantly, these circuits do not work well for highly variable or uncertain steady-state currents. If you have a circuit that draws a lot of power, only when a certain mode is active, which is not active a large portion of the time, or if it has a low power state, then whenever it's in its low power state, the thermistor will cool down and raise its resistance. Then when you transition to the higher power state, the current will rise a bunch and the thermistor, being at high resistance, will significantly droop the rail and possibly cause the whole system to brown out or reset. Additionally, if you have to size the thermistor to be able to handle the maximum current, and it's only running at maximum current a small portion of the time, then the thermistor will have a relatively high resistance at the lower currents, resulting in power losses. Another disadvantage is that it extends the turn-on. What I mean by this is that usually you want to keep the inrush below a certain peak current when designing a soft-start circuit. This circuit will allow you to do that, but as soon as it hits that peak, it starts exponentially decaying with the RC constant of the thermistor cold resistance and the input capacitance. We could theoretically shorten the turn-on time by using a constant current to charge up that capacitance. We'll return to this point later, I'm just foreshadowing right now. There's a significant time delay between the turn-off and the point at which the circuit is reset and ready to accept another turn-on transient. If you turn off the system, then turn it back on only a few seconds later, it will draw a significantly higher inrush current since the thermistor hasn't cooled down yet. Finally, the voltage rise is very slow and takes many seconds before the thermistor series resistance has minimized and the load voltage has stabilized. This can be an issue for lower voltage systems, as often you'll have downstream devices that have their own soft-start circuits that are triggered by the input voltage rising. They might start their soft starts, start drawing some smaller inrush currents of their own, droop the voltage rail, trigger their internal undervoltage lockout circuitry, wait, then start over. The problem is, this tends to happen on the 100 millisecond scale or less, so under these conditions, your subsequent circuits might false start 10 times or more before finally stabilizing. This is generally not a good way to do a clean startup, and so you may need to add components to coordinate power up, thereby defeating the whole purpose of having the low-cost NTC to start with. This slow voltage rise, of course, may not matter at all for many projects, in which case it's merely something to keep in mind while designing. All in all, I'm not a big fan of this circuit, as I prefer to have a low-resistance input power line that is stable post-turn-on. Though if your circuit is AC, its maximum post-turn-on current is pretty low, for example, a 120-volt input under 100 watts maximum, you can find a small NTC thermistor that fits the bill. You aren't too concerned with power efficiency, and your goal is to reduce BOM cost as much as possible, then this is a good option. The second soft-start circuit is a little more complex and deals with a few of the problems that the NTC Thermistor circuit has. This circuit is a resistor and switch circuit. It consists of a series resistor and an electronically controlled switch in parallel with it. At initial turn-on, the switch is open and the resistor limits the current, as with the thermistor. However, in this circuit, once the input current decays a significant amount, the timing circuit triggers the switch to close, and the input resistance of the circuit becomes close to zero. Looking to the right here, we see that the inrush current looks very similar to the thermistor current, initially. However, once the switch is closed, the current bumps up a bit and that voltage drop from the resistor is eliminated by the switch. This makes the steady-state input resistance very low, essentially just the input resistance of the switch, and thus the steady-state system is much more efficient. The switch can be a transistor, a relay, or even an integrated high-side switch circuit designed as a power switch. Today I will use a power MOSFET transistor, as that is typically the cleaner option for DC circuits, though a relay may be necessary for some applications like AC circuits, or if the currents are too large for a transistor. As with the previous circuit, here's an example with a P-channel power MOSFET as our switch, and the same capacitance we used previously. On the gate of the MOSFET we put a resistive divider, leading to an NPN transistor which has a resistive divider from the input rail voltage to ground, with a center tap on the base of the NPN transistor, and a capacitor on its base as well. This resistive divider and capacitor on the NPN base serve as our timing circuit. To the right is a picture of the circuit breadboarded in the lab. So, examining the scope shot I took of the current and a few important voltages, when the 12-volt power is applied, the 4.5 ohm resistor limits the amount of current flowing into the system to a peak of about 2.57 amps, then comes down. Then later on, we see the NPN's base voltage reach about 0.6 volts and stop, implying the BJT has turned on, closing the FET switch as well, causing the difference between the input voltage and the load voltage to abruptly shrink to near zero, and the expected second spike in current, which has a peak of around 1.53 amps. You might be concerned there's a higher spike right at the start of the turn-on that I'm not addressing. However, the spike you see there is actually a digital filtering artifact, though it's worth noting that sometimes there can be a massive spike when the gate drain capacitance is too high relative to the gate source capacitance. We'll discuss that effect when I talk about the final soft start circuit, but in this case it's just a filtering artifact. Here's an unfiltered image of that input current zoomed into the edge, and as we can see, that spike isn't there, at least within the 20 MHz of analog bandwidth my scope was measuring. There may be some tiny spike there due to the source drain capacitance of M1 that my scope isn't picking up because I've limited the bandwidth to 20 MHz, but it's either limited by the inductance or is just so short that it doesn't matter. Anyway, back to the filtered version. We see a spike at 2.57 amps, then it goes down in the familiar RC exponential decay, until at around 65 milliseconds, the current starts spiking up again to another peak of about 1.53 amps. If we look at the yellow trace on the middle plot, which is measuring the base voltage and thus the base emitter voltage of the NPN transistor, we see that this current appears once the transistor gets close to about 0.6 volts. This marks the point at which the NPN transistor turns on and pulls the P-channel power MOSFET M1's gate down and closes that switch. This additional current surge is due to the fact that the capacitance hasn't been charged all the way up to the input voltage. Looking at the third plot on the bottom, we see that the pink trace that measures the load voltage is flattening out a few volts below the 12-volt input voltage trace as time goes on, indicating that its final voltage before the switch turn-on is not the same as the input voltage. This is because the 4.5 ohm resistor and the 39.8 ohm load resistor make a resistive divider with the 12-volt input so that without the switch closing, the final voltage on the output after the capacitors have charged up is only about 10.78 volts, calculating from the resistances of that divider and assuming the cable resistance is negligible. The closing of the MOSFET switch effectively shorts out the 4.5 ohm resistor and triggers another current pulse to charge the capacitance up to the remaining few volts to get up to the input voltage. Now I should talk about why the load resistance in this example circuit is significantly larger than the load resistance in the thermistor example circuit. The reason is because the thermistor circuit needed a large-ish final current of about 1 amp to get good performance out of the thermistor I selected, whereas this circuit has no minimum current requirements, a point in its favor. But also, the circuit does not do well when the non-capacitive load current is high during the turn-on phase. This is because any load current causes a voltage drop across the current-limiting resistor, 4.5 ohms in our case, which is abruptly shorted across when we close M1. As a result, the height of that surge current that occurs during the M1 shortout is determined in part by how large that voltage drop is. If that voltage drop is large, then we might produce a very large current, and our circuit doesn't work nearly as well at limiting the inrush. Additionally, the height of that spike is very dependent upon a few parameters that can be finicky and hard to predict and somewhat unreliable. In this circuit, the height of that spike is determined mostly by how fast the M1 FET turns on, how much resistance is in the path from the 12-volt power source to the input capacitance bank, and the remaining voltage drop across the 4.5 ohm resistor prior to the FET turn-on. The M1 FET turn-on speed is dependent upon the resistor divider there, the capacitance of the gate source junction, to a lesser degree the capacitance of the gate drain junction, and how fast the Q1 transistor is turned on, which depends upon the other divider and the base capacitor. So it can be difficult to determine analytically how high that spike will be, and if it remains within the requirements of your circuit. And it's best to try to minimize the voltage drop across that resistor, as that helps to minimize the spike height overall, and thus our tolerance to its uncertainty increases as well. So this circuit really only works well if that series resistance is not dropping the voltage much after the input capacitance is charged, when the only current is steady-state non-capacitive current. This is good for circuits that don't draw a lot of steady-state current or only switch on to higher power modes much later after post-turn-on. However, it does present a difficulty if the circuit always draws lots of power. The thermistor got around this by slowly changing its resistance over the course of several seconds, which slowly charged the capacitance and didn't cause a secondary surge current. You can replace the series resistance in this circuit with a thermistor. However, since thermistor heat-up timescales are on the order of seconds to tens of seconds, you might need a different timing circuit than the one used here, as using this type of timing circuit would require a massive base capacitor to get a 10-second delay before the base turn-on, even with a 10 megaohm resistor. Those caveats aside, though, this circuit does limit the initial surge, and once the switch is closed, the input voltage is the same as the output voltage, minus a small drop from the switch resistance. This means the downstream circuitry can draw significant currents and have very little voltage droop on the load voltage. This voltage difference between the input voltage and output voltage can be made to be significantly lower than the NTC case if a MOSFET with a very low drain source on resistance is chosen. And MOSFETs with drain source on resistances lower than 50 milliohms are relatively inexpensive and plentiful. So let's take a look at the advantages and disadvantages of this circuit. So this circuit's biggest advantage of the NTC version is that it has a very efficient post-turn-on state where it's got a nice MOSFET or relay resistance as the only resistance in series with the power line. That resistance also doesn't increase if the load current decreases. So this circuit accommodates highly variable post-turn-on currents. The circuit does not get hot, so long as you size the FET or relay to be large enough, and the thermal environment doesn't affect the circuit's performance significantly. It resets fairly quickly. The timing circuit I use should be pretty well reset by about half a second. The source gate voltage should drain through the 100K resistor well before then as well. Though note that the bigger you set the values to increase the turn-on delay for that particular timing circuit, the longer it will take to reset properly, and if you want to reset more quickly, you might need to make a more complicated timing circuit. This circuit also works for both DC and AC circuits. The version I presented does not work for AC circuits. You need to use either a relay or a pair of FETs to create a bidirectional switch. Also, the timing circuit would need to be modified to accommodate an AC circuit, but it can be done and without much fuss. For disadvantages, the post-inrush steady-state load current has to be much lower than the max inrush requirement. Without that, as discussed, the voltage drop across the switch at the time the switch is closed will be too high, and the resulting secondary current spike might be massive and render the whole circuit worthless. Alternatively, you can use a thermistor to make a hybrid of this circuit with the thermistor circuit, but the timing circuitry becomes a little more complex to design, especially while keeping a reasonable reset duration. Note that once the switch is closed, the load currents can be high, low, or highly variable. It's just that the load current after the capacitance is charged, but before the switch is closed, needs to be much lower than the max inrush requirement. It's definitely more complex than the thermistor solution, requiring a separate timing circuit and several more components. Like the thermistor solution, it extends the turn-on longer than necessary since it still relies upon charging up the capacitors with an exponentially decaying current draw. I wonder if the third circuit will have this disadvantage. Along with being more complex, it's more expensive than the thermistor solution. And the behavior of the current when the switch turns on can be a little difficult to determine, as the peak current there is a function of many different parameters, including the inductance and resistance of the cabling and capacitor bank, as well as how fast the switch is turned on. Now we move on to the final, and my favorite soft start circuit of the video, the ramp rate controller circuit. This circuit is designed to take an abrupt or uncertain application of voltage in and create from it a gradual voltage rise with a constant linear slope from 0 volts to V in. Here's a rough schematic for the ramp rate control circuit. For most situations, you want to control the ramp rate on the positive rail and leave the ground rail alone. And as such, I put a P-channel MOSFET here. You can create the mirror of this circuit with an N-channel MOSFET on the ground line, but that tends to be only for niche applications where you really need the additional performance of an N-channel MOSFET and can handle adding resistance to the ground line, so we'll not discuss that here. The ramp rate control circuit requires using a MOSFET as its workhorse transistor component. Technically, a BJT, JFET, IGBT, or other similar component would probably work, but in the vast majority of circuits, a power MOSFET is preferred. It is important to note that a relay or other device that does not have a transition region between closed and open will not work here. The MOSFET works in conjunction with a gate-drain capacitance, denoted by C1, to produce a near-constant turn-on voltage slope on the output. This results in a roughly constant slope voltage output rise and a current input that starts at 0, then bumps up to a near constant value determined by the capacitance and the output voltage slope, then drops down to the steady-state output current at the end. The flat region of the current during turn-on will actually be a little different depending upon the current draw of the downstream circuitry during the turn-on phase. So this diagram and the testing we're going to do in the lab will be assuming the majority of the inrush is into the C-in capacitance, which is often a reasonable assumption. However, it will work fine if there's significant non-capacitive inrush current. The shape of the current waveform will just look different than this diagram here and the results from the lab. So we have a pretty nice voltage waveform that comes up in a programmed time period. We have an inrush current that can be pushed to the maximum of our requirement and kept near that value for most of the turn-on period, rather than spiking up to that value then exponentially decaying. This allows shortening the time period that the turn-on occurs. Best of all, this circuit works for large load currents, small load currents, and everything in between, and as a bonus, it requires fewer components than circuit number 2. So how does this all work? To understand that, we need to first go over the details of what happens as power MOSFETs turn on. First, let's isolate the MOSFET and label some voltages and currents. So here we have drain current, source drain and gate voltages, and 2 capacitors, the gate source capacitor and the gate drain capacitor. Note that I've removed C1 and C2 from the previous schematic. These capacitors here are internal capacitances of the MOSFET itself. There's also an internal capacitance between the source and drain, but it isn't really important for this particular discussion of turn-on and will only serve as an unnecessary complication. To simplify the gate charging source, we're going to assume there's a current source with a constant current that is off at the start and turns on right at time t equals 0, where the current starts flowing through it jumps from 0 to a value noted as I charge. R1 we will assume is very large and is only there to ensure that Vg is the same as Vs at the start of this thought experiment, and currents through it will be ignored thereafter. In fact, we'll just remove it entirely from the schematic once I charge starts. So at the start at time t equals 0, the source voltage Vs is at 12 volts, the gate voltage is also at 12 volts, and the drain voltage is at 0 volts, due to the capacitive load and some resistive load to ground off-screen to the right of the ... The current source switches on and I charge starts flowing, but since no time has passed yet, the voltages all remain the same since the capacitors have to be charged for any voltages to change. As time marches on from 0 to T1, current flows out of Vg through I charge into ground. So as current flows out of Vg, this causes Vg's voltage to start dropping as CGS and CGD are charged up, creating a voltage difference between gate and source, and by extension, gate and drain. Neither the drain voltage nor the source voltage are changing because the source voltage is connected directly to a voltage source, pardon the wordplay, and the drain is connected to a massive capacitor off-screen, downstream of the drain, and so the tiny current through CGD, which has a capacitance that is orders of magnitude smaller than the load capacitance, isn't going to move the drain voltage appreciably. In order to determine what happens next, we need to get the gate threshold voltage of this part. This part I've selected for this circuit is onsemi's FQP27P06, which has a range of -2 volts to -4 volts for VGS threshold per its datasheet. Note that negative in the datasheet is because they're quoting VGS, and the gate has to be lower than the source in order for a P-channel MOSFET to turn on, the opposite of an N-channel MOSFET. I often tend to switch to VSG under these circumstances, as it helps intuitively for me if the voltage that drives MOSFET turn-on is a positive number. We'll assume the threshold for our M1 is right in the middle of the specified range for this part, or about 3 volts VSG. Once we hit this threshold, drain current starts to flow, starting with 250 microamps based on the datasheet, but it won't take much more VSG voltage to make much more current flow. Now here's the interesting part. We can assume that because the power MOSFET is so large, that tiny increases in VSG will cause huge increases in drain current. This means that we can assume that the drain current will go from about 0 amps to something huge like 10 amps with virtually no change in VSG. This is only a rough estimate, and so will only provide a rough approximation of the results, but this assumption significantly simplifies this circuit and helps us to make a first-cut prediction of the behavior of the circuit. We can always refine it later. This assumption you're making is that, essentially, the transconductance of the MOSFET is infinity for VSG values greater than the threshold voltage. So now VSG is fixed, VS is fixed, and current is flowing through ID. The current I've drawn here is for a mostly capacitive load drawing a current of I1 during turn-on. Interestingly, under these conditions, it mostly doesn't matter what the load is. It could be a resistor, a capacitor, a combination, or a current source type load that turns on above a certain voltage. So how do we calculate the value of the drain voltage with respect to time in this plateau region? Well, we know that if VG drops by a tiny bit, the current ID goes to infinity, essentially. So in order for ID to be finite, VG must be constant. If VG is constant and VS is constant, then no current flows through CGS. We only have 2 currents left on the gate node, I-charge and IGD. Since VG must remain the same, I-charge and IGD must be equal to each other. And we know from the nature of capacitors, the expression for IGD is CGD times dVdG dt. Note that since VG is constant during this time, VdG simplifies to VD, and so this becomes IGD equals CGD times dVd dt. And thus I-charge is equal to CGD times dVd dt. Rearranging to get the derivative on the left, we get dVd dt equal to I-charge over CGD. We know I-charge is a constant, and we assume CGD is a constant, though in reality this is only a very rough approximation. This means we can directly anti-differentiate dVd dt, and we get Vd is a line with constant slope of I-charge over CGD. So Vd is just an upward sloping line that starts at 0 volts at time t equals t1 and ends at 12 volts when t equals t2. The equation is only valid from between t1 and t2. Prior to t1, the voltage is 0, and after t2, the voltage is 12 volts. This effect of the output voltage feeding back current into the gate is part of an effect called the Miller effect, which is why we call this flattening of the gate voltage during turn-on the Miller plateau. We won't discuss the Miller effect in any more detail in this video, though this explanation does cover a lot of the basics. After Vd reaches 12 volts, the gate voltage will start dropping again, which will only have the effect of further reducing the drain source on-state resistance, or RDS on, but no more significant effect than that. The current due to charging the capacitors goes away and drops to the non-capacitive load current, represented here as I2. We have now reached the on-state, and this region onward is considered post-turn-on. So already we see that for a constant gate charging current, we get a constant voltage slope turn-on, and all it depends upon is the value of that gate charging current and the gate drain capacitance. This is exactly the behavior we want, though the timescales for a MOSFET turning on in this manner without additional external capacitance tend to be pretty short, and the current surge tends to be very high. Also, it's worth noting that the most dubious assumption we've made here is that CGD is constant. It is not. It changes with respect to VDS to a significant enough degree that when calculating MOSFET turn-on behavior, we usually want to use the total gate charge rather than the actual capacitors, because the capacitors change so much during turn-on that it's simpler just to assess the total charge that must flow into the gate during turn-on. But we can do a simple if brutal way to linearize this gate drain capacitance, which is simply adding a much larger capacitance in parallel to it that swamps out the variations and makes them negligible. This generally has the downside of slowing down the turn-on of the FET, but for this circuit we actually want that turn-on to be pretty slow, on the order of milliseconds at minimum, and so this will usually not be a problem. Now that we've gone over MOSFET turn-on, we move back to the main soft-start circuit. Here I've folded the parasitic capacitors CGS and CGD back into the MOSFET so they're no longer explicit, and C1 and C2 represent additional physical capacitors placed into the circuit. C1, as we said, serves to increase and linearize the gate drain capacitance, and C2 is an important capacitor that will be discussed later. Also, instead of a current source, we have a simple resistor divider on the gate. So the main difference between the previous circuit and this one is that we have a resistive divider rather than a current source. Fortunately, our assumptions make this a non-issue, as we will soon see. Looking back at the plots from the MOSFET turn-on, the two regions where VD is static, right at the beginning and right at the end, will look a little different since the charging of the capacitance of the MOSFET will follow an exponential rather than straight line, because of the resistive divider being the charging force rather than a current source. However, during the Miller Plateau region, we can see that the resistive divider will have three static voltages connected to it during the turn-on period. Vn on the top equal to 12 volts in our example, Vg on the middle equal to 12 volts minus the threshold voltage of 3 volts, equaling 9 volts in our example, and ground or 0 volts on the bottom. This means that the current flowing out of the divider will be constant during turn-on, and thus functionally equivalent to a current source. Thus we have a very similar situation to the one we just went over. So first, let's construct the Thevenin equivalent circuit for the resistive divider for just after 12 volts is applied to Vin. At this point, Vin will always be 12 volts and ground will always be 0 volts. So for a simple resistive divider like this, the Thevenin equivalent voltage is Vn times the voltage divider ratio, and the Thevenin equivalent resistance is the parallel combination of R1 and R2. There are a few reasons to use a divider instead of just a resistor to ground. First, the value of Vn may be close to the gate source breakdown voltage of your FET. Most MOSFETs have gate voltage breakdowns of 8, 10, 15, 20, or 25, with the vast majority being either 10 volts or 20 volts. This means that if your input voltage is close to the same value as your gate source breakdown voltage, and you are concerned about voltage spikes appearing on that gate voltage, you will want the maximum voltage applied to that gate to be less than Vin. The divider allows you to set that maximum voltage. Second, it impacts the charging circuit by setting the charging voltage. But most importantly, it allows a direct, easy-to-see discharge path between gate and source that ensures that the circuit will reset when the power is cut to the circuit. So now that we have this Thevenin equivalent circuit constructed, let's treat this circuit a little differently and actually do a little design for our inrush application with a few requirements. First, I've chosen the MOSFET already to be the onsemi FQP27P06, so we'll treat this as a requirement for simplicity's sake. Second, we want the inrush current to be less than 5 amps. Third, we want the input capacitance to be the same as the 4720 microfarads I had in previous circuits. And lastly, let's set the load resistance to approximately 40 ohms, resulting in an on-state current of about 300 milliamps. This is a simple set of requirements with which to design our circuit. So now let's recall the range of threshold voltages for the onsemi FQP27P06 is VSG of 2 volts to 4 volts. We'll again assume a threshold voltage of VSG of 3 volts. I'm going to set R1 to 1 megaohm because I already kind of know what my values will be, and 1 megaohm is about as large as you'd want to go for R1 to still have it be a capacitor bleed path. In general, you may need to do an iterative design process to eliminate this degree of freedom. So looking back at the inrush current of less than 5 amps, with my input capacitance at around 4720 microfarads, we can calculate the dVdt that causes 5 amps to go into the capacitor by using the formula IN equals C dVdt. So 5 amps divided by 4720 microfarads equals dVdt equals 1059.3 volts per second. That's our target voltage rise slope. This will cause the turn-on to take about 11.33 milliseconds. Pretty nice and fast compared with the other two soft-start circuits. Now it's worth noting that this does not take into account the current drawn by the load resistance. While this is true, the resulting circuit will very likely be slower than our estimate due to the assumptions we have made, but even if it isn't, we can reassess in test. So let's go with a target of an even 1000 volts per second, a nice round number. So to design this target, we need to know IDiv, which involves setting RDiv, and we need to set C1. This is too many degrees of freedom. So let's set C1 to something like 10 nanofarads to eliminate a degree of freedom. This should work because 10 nanofarads is around 10 times the parasitic CGD capacitance of the FET at low drain source voltage, and thus it will swap out most of the variations. And it's not too large, so that means, for reasons we'll get to later, that we don't have to make C2 very high. So now that we have C1, we need to calculate the charging current. Recalling this expression for the slope of the drain voltage rise time, we just rearrange it to solve for charging current. Then we plug in the 1000 volts per second slope we calculated earlier, and the 10 nanofarads C1, and we get a charging current of 10 microamps. Now we need charging voltage. To get that, we take the gate voltage at the plateau, which is just Vin minus the VSG threshold voltage, and subtract that from Vdiv. We take the charging voltage and divide it by RDiv to get another expression for the charging current. Doing a bunch of algebra I'm not going to show, we use these two expressions for charging current to get an expression for R2 in terms of known values, which, when plugging in our known values, we get approximately 692.3 kiloohms. I'm going to set R2 to around 500K by using two 1 megaohm resistors in parallel. This is somewhat near the value we calculated, but a fair bit off. As a result, this will increase the charging current to 15 microamps and thus increase our predicted dV out dt to about 1500 volts per second. However, I suspect, mainly because I've already verified it in the lab, that this will not break our requirement. In general, this method is likely to predict a higher peak current than reality, especially since the plateau voltage will be a bit lower than the threshold, as a significant amount of current will be flowing through the drain at plateau, and it takes a volt or so before the FET truly gets high transconductance. So let's move forward with the setup and we'll reevaluate if the lab results prove too high of a current. Finally, I set C2 to 100 nanofarads, which I'll explain later. Okay, now let's take a look at the completed circuit. Here's an image of what I rigged up on my breadboard in the lab. The switch in the schematic is just me pressing two wires together and taking scope shots until I get one where the switch bounce doesn't significantly affect the circuit. So measuring the current with a current probe, and the three FET voltages with voltage probes, I get the following results filtered and decimated to clean up the signals. Here we see the rough profile we outlined before, with the gate voltage falling initially, though in an exponential decay, not a linear one as with the current source. Then flattening, coinciding with the drain voltage rising with an approximately constant slope. Then, once drain voltage reaches the same voltage as the source, indicating turn on is over, the gate voltage again continues to drop in an exponential decay and flattening out at the final Thevenin equivalent voltage of the divider. The slope of the rise time measured from 25 milliseconds to 40 milliseconds is about 540.8 volts per second. We see the current spike up during the turn-on with a 2.867 amp peak, and then drop down to a steady-state current of about 316 milliamps. So the general form of the circuit appears, but the values are a fair bit off from what we expected. On the bright side, the values are below our requirements, so we still meet our requirements as we didn't have a requirement limiting how slow the system could be, and it's still pretty fast. The turn-on time of the voltage ramp is less than 50 milliseconds all told. Taking a closer look at the gate source voltage directly, since the gate voltage doesn't account for some of that source droop we were seeing, we see that the source gate voltage is not flat, and in fact, during the center of the rise time, it's sloping upward slightly. This breaks our assumptions significantly and causes a current to flow through the gate source capacitance. Since the gate source capacitance is much larger than the gate drain capacitance, then even though the VSG slope is gradual compared with the VGD slope, it will still present a significant error and slow down turn-on. Additionally, the plateau voltage is much larger, 4.7 volts VSG rather than our assumption of 3 volts. This makes the overall gate voltage closer to ground during the turn-on, which reduces the charging current, and thus also makes this output slope more gradual. We also haven't closely examined the nonlinear behavior of the parasitic capacitors of the FET, nor have we dealt with errors in the component values, especially frequency-dependent ones. Additionally, the setup is a breadboard without a ground plane, which may have hidden parasitics, adding even more errors. As a result, getting an accurate turn-on rate from the analysis from this kind of circuit requires a great deal more detailed analysis to produce. As detailed analysis tends to be time-consuming and testing this kind of circuit is generally pretty easy to do, it is simpler to do a rough design, then test the circuit and tweak the values as necessary to get the result you want. Rarely do you need a soft start circuit that must turn on with a very specific turn-on rate and time constraining you. You can typically just design the inrush to be lower than specified, then make sure with testing that component deviations and non-idealities in your assumptions don't cause it to be too high. Now let's briefly look at the turn-off waveform. Here we see that when I disconnect the source voltage, the source and drain exponentially decay due to the RC circuit made with the load resistance and load capacitance. The gate voltage also decays down. The reason the source voltage isn't zero is because of the FET's body diode effectively keeping the source voltage from going much below the drain voltage. Obviously, the turn-off profile will depend upon the specific load currents and capacitance of the system you are using, but this is good as an illustrative example. Taking a closer look at the source gate voltage itself on the bottom plot, here we see it drops to below its minimum specified threshold at around 300 milliseconds. All this indicates that barring an extremely slowly falling load voltage due to ultra-high load capacitance and ultra-low load currents, the system will shut off and the soft start circuit will reset in well under a second. Compare that with the tens of seconds required for the thermistor circuit. It's worth mentioning at this point that one consideration you should be aware of when implementing a circuit with a power MOSFET that spends greater than about 10 microseconds in its transition mode between fully off and fully on, you need to make sure it stays in what is referred to as its safe operating area. Essentially, while a MOSFET will have a simple maximum current rating, that current rating is intended only for when the power MOSFET is fully on. During the transition region, the effective resistance and amount of power a MOSFET burns is significantly higher. Since resistance is highly nonlinear for a MOSFET, the more direct method of describing power dissipated is to multiply the voltage drop across the drain and source by the current through the drain. We have to make sure that during turn-on, the power dissipated isn't too high for too long. Determining this with just the maximum allowable temperatures, the maximum current rating, and the various thermal impedances, etc., would be very difficult, if not impossible, to do. So fortunately, most MOSFETs have a plot for a safe operating area provided in the datasheet. The one for the FQ-P27P06 is shown here. Here we see it's a log-log plot with drain source voltage on the x-axis and drain current on the y-axis, with a few curves for different durations, creating a sort of box area. The edges of this box show that you can never allow more than about 100 amps through the FET no matter what the voltage drop is, probably 108 amps looking at the table on the left. It also indicates you can always allow at least 2 amps through the FET no matter what the duration or drain source voltage you have within its breakdown limits. Though plots like these usually assume a fixed part case or junction temperature, and so the plot assumes good heat sinking for the longer durations. This one assumes a case temperature of 25 C and a maximum junction temperature of 175 C, and that for the durations other than DC, it lasts for a single pulse with a long period of time between pulses, so that the FET is relatively cold before another pulse happens. Note that a case temperature of 25 C means that you need really good heat sinking to keep the case at 25 C if your room temperature is something like 20 C, as 5 C is not a very big temperature difference between a FET burning a bunch of power and the room's air. Inside this box, we see things like 100 microseconds, 1 millisecond, 10 milliseconds, and DC. The FET will be safe within those regions for up to those durations. For example, if your drain source voltage is at 20 volts, you can have a current pulse as high as 100 amps if the pulse width is less than 100 microseconds, up to around 55 amps if the pulse width is less than a millisecond, 20 amps if the pulse width is less than 10 milliseconds, and up to 6 amps if the pulse width is longer than 10 milliseconds. You can sort of roughly interpolate between the curves if you have different durations, though it's best to make conservative estimates when you can and just get a bigger MOSFET if you really need a bigger current spike. For the circuit I made, the easiest way to assess if we're in the safe operating area is we start with a more worst-case approximation of the shape of our current and the drain source voltage during turn-on. So we might say it was a 50 millisecond turn-on period where VDS is 12 volts and the current is 3 amps. This does not reflect reality as VDS gradually goes from 12 volts to 0 volts, and the current is only significant for about 25 milliseconds and only around 3 amps for 20 milliseconds. But this conservative estimate allows us to easily look at this plot to see if we're within the safe area. If we're not in the safe area but we're close, then we make a slightly more refined estimate and see what that looks like. Or we use another FET or change the soft start values to reduce the peak current. Looking at the plot for our FET, we see that for a voltage of about 20 volts, the maximum current allowed for any duration is 6 amps. Since our conservative estimate was 12 volts and 3 amps, we're well within the maximum value even under our excessively conservative assumptions. So our soft start circuit is within the safe operating area. Before we conclude with this circuit, there is one final very important thing we need to discuss that can cause a big headache if you do not keep it in mind when designing circuits like this: the necessity of this 100 nanofarad capacitor on the gate source junction. The gate source junction capacitance hasn't been discussed much thus far, apart from causing an error from our assumption that the Miller plateau is flat when in reality it is not. One would think minimizing this gate source capacitance would be best to minimize this error. However, there are two other more important effects. First, the gate source capacitance along with the gate drain capacitance increases the amount of time from the turn-on of the V-in voltage and the plateau due to the time required to charge up this capacitance. And so if you need a longer delay, you can increase this capacitance a little at the expense of increasing the Miller plateau flatness error. However, more importantly, this gate source capacitance forms a capacitive divider with the gate drain capacitance that determines the gate voltage right after power is applied. To show what I mean by this, let's think about this circuit right from the point at which the V-in is applied. We'll assume a very small time frame. The source equals 0 volts at the start, and the switch gets closed extremely quickly so that the source is set to 12 volts in less than a microsecond. We'll also assume there is no significant inductance in the system. So, with such a sharp turn-on, the impedances of the capacitances are very low, and the relative impedances of the resistances are extremely high. Additionally, the drain-to-ground capacitance at the load is assumed to be so many times larger than the gate drain or drain source capacitance that we can essentially treat the drain-to-ground capacitance as a short. So the drain is shorter to ground, and the circuit really looks more like this. A simple capacitive divider. I've labeled these two capacitors as CGS prime and CGD prime, where each is the combination of the internal gate source or gate drain capacitance and the external gate source or gate drain capacitance. So now that we have this, let's calculate VSG right after power up. VSG is equal to VS minus VG. VG is determined with this capacitive divider. Here I've used Z's to denote the impedance of each capacitor. As the whole thing is capacitive, all the Laplace variable S terms, which could also be written as j omega terms, cancel out, and when you go through the rest of the math, you get VSG equal to VS times CGD prime over CGD prime plus CGS prime. So to illustrate how this might present a problem, imagine you set CGD equal to 10 nanofarads as we did, which makes CGD prime about 10 nanofarads as well, but didn't put that additional 100 nanofarads of gate source capacitance. The gate source capacitance of the MOSFET varies widely over various conditions, but based on the datasheet, it's pretty safe to say that it's less than 3 nanofarads under our conditions. So let's assume a CGS prime of 3 nanofarads. Recall our V-in voltage is 12 volts and our VSG threshold voltage is assumed to be about 3 volts. The resulting VSG at turn-on per this formula, with a V-in of 12 volts, is 9.231 volts, which is well above the threshold of 3 volts. This would cause the MOSFET to turn on very quickly, causing the drain voltage to jump up and cause a surge of current. This actually breaks our assumption of VD being equal to 0, since the FET turning on will bring that voltage up, and so we have to make a slight adjustment to the equation to get VSG for non-zero VD, and under these circumstances, VD would jump up to about 8.1 volts before that effect would bring VSG back down to the threshold. So the output voltage would not go all the way up to 12 volts. However, a near instant jump of 8.1 volts obviously triggers a surge of current to charge the capacitor, which defeats the entire point of the soft start circuit. So, to make sure you don't cause any spurious turn-on, make sure that this capacitive divider, along with your maximum expected input voltage, results in a starting VSG of less than the threshold voltage. I generally drop it lower than the threshold by a significant amount for margin and to give a little time after the application of Vin for Vin to stabilize before the FET starts turning on. Hence why I chose a 100 nanofarad capacitor for the gate source voltage, which results in a VSG of 1.091 volts at initial turn-on, well below the 3 volt threshold. Now let's go over the pros and cons of this circuit. So first off, we get a tunable peak current control with just changing some resistor and capacitor values. It has the minimum turn-on time when faced with a peak current requirement and thus allows the start-up period to be minimized, which may be especially helpful when secondary circuits down the line need to start up. It does not get hot, assuming you chose your MOSFET properly. It controls the voltage ramp-up speed. Some ICs require a specific range of ramp-up speeds, and if you're outside of that range, either too slow or too fast, it can improperly reset or get damaged. This allows you to specifically design a ramp-up speed and thus satisfy exotic requirements like that. It has a very low on-state resistance, that of the closed MOSFET switch. It resets quickly. It accommodates highly variable or uncertain post-turn-on currents, not requiring a minimum post-turn-on current to keep it low resistance like the thermistor. And the thermal environment has no significant impact on it like the thermistor. On the disadvantages side, it's slightly more expensive than the thermistor solution, though probably the same cost or maybe even a little less expensive than the resistor and switch solution. This circuit is a little more complicated than the other circuits. But perhaps its greatest drawback is that it doesn't work on AC circuits unless you have to use one of the other circuits, or even another circuit not covered in this video, if your application is an AC circuit. So now that we've discussed all three circuits, let's look at all three and note under what conditions they're each the most optimal design choice. The NTC thermistor is best used when you have low current circuits that have stable post-turn-on currents that don't vary much after turn-on, and where low cost and simplicity are the most important attributes and efficiency is less important. The resistor and switch is best for AC circuits that need to be efficient, or have large or widely varying post-turn-on currents, or a slightly simpler design for a DC soft start circuit than the ramp rate controller. The ramp rate controller is best for DC circuits that need to be efficient or have large and or widely varying post-turn-on currents, and the extra complexity in the design is worth the improved performance and slightly lower cost when compared with the resistor and switch. That concludes this video. This video was a sort of spotlight on a circuit that is talked about a little less in textbooks, but is nevertheless very useful. If you have suggestions or requests for videos spotlighting other niche circuits or special applications like this one, please leave a comment. Thank you for watching the video. If you enjoyed it, please like, share, and subscribe. If you have any comments or questions, leave a comment. See you next time.